Hi everyone, I'm Qin Chen from National Yangming Chiao Tung University, and today I'm very happy to present our work, PromptTSS, a prompting-based approach for interactive multi-granularity time series segmentation. This work has been accepted by CIKM 2025, and it's a collaboration between National Yangming Chiao Tung University and GoH.ai. In this talk, I'll share about how we use prompting to make time series segmentation more flexible and interactive, especially when dealing with multiple levels of granularity. Let's start with something we all see every day. Time series data are literally everywhere, from smartwatches tracking our heart rate, to smart homes recording sensor readings, to industrial machines and web dashboards logging performance metrics. All of this generates continuous streams of data that change over time. But raw signals themselves don't tell us much. To make sense of what's actually happening, we need to break these signals down into meaningful parts. And that's exactly what time series segmentation is about. So what is time series segmentation? Think of it as dividing a long continuous signal into chunks, where each chunk represents a distinct state, like sitting or moving. We start with the raw signal, shown here at the bottom, and the goal is to infer the underlying sequence of states above it. In other words, segmentation helps us understand when and how the states change over time. In reality though, things aren't always that simple. Many real-world signals have multiple levels of granularity. For example, at a higher level, we might describe the activity as move, but within that, we can have more specific actions like walking, running, or jumping. So, instead of one flat segmentation, we have a hierarchy: core states describing general activities, and fine states capturing detailed variations. Handling both levels together, that's what we call multi-granularity time series segmentation. There are already many time series segmentation methods out there, but most of them work at only one granularity level. Now let's look at the first challenge, the inability to handle multiple levels of granularity. Most existing models can't handle multiple levels within a single framework. They need to train one model for coarse segmentation and another for fine segmentation, which means we end up with multiple models instead of one unified model that can capture both the overall trend and the detailed variations. As a result, these approaches fail to represent the full spectrum of patterns in real-world time series. Now that we've seen the first challenge, let's look at the solution to the first challenge, prompting. The main idea is that instead of training separate models for coarse and fine levels, we train a single unified model that can handle all granularities. We simply tell the model what kind of segmentation we want through prompts. In PromptTSS, there are two types of prompts, label prompts and boundary prompts, and each of them can be positive or negative. Label prompts provide hints about what the state is or isn't at a specific point. For example, we Now let's move on to the second challenge, limited adaptability to new patterns. Most existing segmentation models are static. They are trained on one dataset and work well as long as the data at test time looks similar to what they've seen before. But in real-world environment, time series patterns often change over time. For example, in manufacturing or financial systems, new behaviors, operating conditions, or anomalies can appear that were never seen during training. When that happens, these models struggle to adapt. Their segmentation rules become outdated, and they can no longer correctly identify the new or evolving state. As a result, the model's performance drops, and it fails to keep up with the dynamic nature of real-world time series. Now let's look at the solution to the second challenge. And yes, it's still prompting. To address the problem of limited adaptability, we let the model receive prompts even during inference. This means that when the model encounters new or unseen patterns, users can provide a few label or boundary prompts to guide it. For example, if the system starts showing a new type of behavior that wasn't in the training data, we can give the model small hints through this prompt. The model then uses this information to refine its prediction in real time, instead of relying only on what is learned during training. This prompting mechanism allows the model to continuously incorporate new information and dynamically adapt to evolving patterns, so it can stay accurate even when the data distribution changes. This slide shows the overall framework of PromptTSS. As we can see here, the model takes two inputs, the time series and the prompts, and produces one output, which is the predicted sequence of states. The time series is first processed by the time series encoder, which converts the raw signal into embeddings that capture temporal patterns. At the same time, the prompt encoder processes the label and boundary prompts into embeddings that represent user guidance. These two embeddings are then fused by the state decoder, which generates the final state predictions. Next, we'll take a closer look at each of these three components, the time series encoder, the prompt encoder, and the state decoder, to see how they work together to achieve interactive multi-granularity segmentation. Now let's take a look at the first component, the time series encoder. The input time series is often very long, and feeding the entire sequence directly into a transformer will be computationally expensive. To make this more efficient, we first apply a process called patching, where we group a Now let's look at the second component, the prompt encoder. We have two types of prompts, label prompts and boundary prompts. Label prompts tell the model what the state is or isn't at a given time, while boundary prompts indicate whether a state change happens at that point. For Now let's move on to the final component, the state decoder. The state decoder takes the embeddings from both the time series and the prompts, and fuses them to predict the final state sequence. Now let's talk about the training strategy. Here we use the iterative training. PromptTSS is designed for interactive segmentation, where the user can provide prompts step by step to refine the model's predictions. To simulate this interactive behavior during training, we also train the model in multiple iterations. At the beginning, the model starts without any prompts and makes its initial prediction. We evaluate PromptTSS on 8 real-world datasets covering both industrial process and human activities. Among them, Industry MG is a real-world multi-granularity dataset that naturally contains both coarse and fine-state annotations. We also create coarser versions of several datasets, such as 2 times and 4 times coarser versions of the PUMP datasets, to study multi-granularity segmentation. Together, these datasets provide a comprehensive benchmark for evaluating PromptTSS across single and multi-granularity settings. Here we show the overall segmentation performance of PromptTSS compared to existing methods. On the left, we have multi-granularity segmentation, and on the right, single granularity segmentation. Across both settings, PromptTSS consistently achieved the best performance, shown here in blue. In a multi-granularity case, we can see that PromptTSS outperforms all baselines by a clear margin on every dataset. This shows that our unified prompting framework effectively handles both coarse and fine states within the same model. For single granularity segmentation, PromptTSS still maintains strong accuracy and generalization across all datasets, demonstrating that the prompting mechanism not only supports hierarchical segmentation, but also improves standard segmentation tasks. Now let's look at the transfer learning results. Here, we evaluate how well PromptTSS can generalize to unseen datasets and unseen granularity levels without retraining. In the top section, we train the model on one dataset, such as Pump V35, and test it on another, like Pump V36 or V38. PromptTSS achieves much higher accuracy and F1 scores compared to all baselines, showing that it can adapt to new datasets with only a few prompt inputs. In the bottom section, we test transfer across different granularity levels. We've made our code available on GitHub. Feel free to try our framework yourself. That concludes my presentation. Thank you all for listening, and if you're interested in learning more about this work, you can scan the QR code here to visit my personal website.